Assalamu alaikum, Bismillahirrahmanirrahim. So today we will start our lecture number 5 and 6. In the last 2 weeks we have covered lecture 1 and 2 and 3 and 4. 1 and 2 is related to basic introduction of the course and thermodynamic introduction, and lecture 3 4 related to the some numerical of pressure. So we will start this lecture with the one numerical that is related to your core discipline, civil engineering. So I select this numerical. This is addition to that numerical of pressure. So it pillar of the we start the numerical. Pillar of the house building supports on a concrete floor which withstand 5 kilopascal pressure. In the live session, student asked me the question related to how the force is converted into the pressure when we apply the force. So I told that on the solid surfaces it produce opposite and equal reaction. So the force is constant in the solid portion. If you transfer the force in the solid object, it transfer the same amount of force in its other end, or as a opposite and reaction force. But the pressure can be changed by decreasing or increasing the area. So we get the advantage of we know that how the application can be done in this way. So in the same way, this is question related to the building construction, in which the question is telling us that a floor of some building or concrete floor of a building can withstand 5 kilopascal of pressure. As per building weight distributed on the pillar is of 1 ton, and this is like I just draw this concrete slab or concrete floor in which this pillar need to be withstand, but the pressure which this concrete floor withstand is 5 kilopascal. So we need out to determine the minimum imprint area of the pillar. So we need to calculate the minimum area. Maximum area can reduce the pressure, and we can easily withstand heavy weights, but we need to calculate the minimum area to reduce our further pillar weight and pillar quantity, pillar volume. So we apply the same formula. Pressure is equal to force upon area. In S note, this S note can be saved, and I will also share with slides folder. So we apply pressure is equal to force upon area, and how much the force is 5 kilopascal. So we can write directly 5 10 to the power 3 Pascal, because by this formula the equivalent force can be calculated in the unit of Pascal, that is as a unit of pressure. How much the force is equally of weight, and the area we need to calculate. So how much the force is applying by the pillar, its own weight, that is telling in the numerical. So by opening weight is equal to mass multiplied by gravity, and we can place area over here and divide by the pressure 5 10 to the power 3. So area how much the weight is 1 ton. 1 ton is equal to 1000 kg. 1000 kg and multiply by 9.8 meter per second square divided by 5 10 power 3. This can be cancelled out with this, and 9.8 divided by 5 is 1.96 meter square. So this is the minimum area we required by the pillar to withstand on the concrete floor. If we reduce the area, less than this value, then it can break the concrete floor. But if we increase, then it will be safe. Normally we kept factor of safety around more than 2, but in different application, critical application, the factor of safety can be more than 2. So now move on the another topic. Then the last slides of the lecture 4, we cover the parameter. One of the property of important property of thermodynamics is that is temperature, and the law related to the temperature is zeroth law. That already has been explained in the last lecture, but here I again put this topic because I found very good animation regarding zeroth law. So after this slide we have a video of zeroth law. You can.
What is the zeroth law? Equilibrium. And to demonstrate thermal equilibrium, let's say you had a piece of pie, key lime pie, and you also had a steel sphere. And we're going to take this steel sphere and I'm going to place this in thermal contact with the pie, which is to say they can exchange heat. And which way is the heat going to flow? We know the heat will flow from the hotter object to the cooler object. Let's say our pie was in the freezer, it's nice and cold, and our sphere was sitting at room temperature, so it's the relatively hotter object. Then we know heat will flow from the hot object to the cool object, which is to say heat will flow from the steel sphere into the pie. But this net exchange of heat stops at some point. At some point the sphere heats up the pie enough that no net heat is transferred one way or the other, and basically you just have a pie and a steel sphere sitting there and no net heat is transferred. And when that happens, when no net heat gets transferred between two objects, we say they're in thermal equilibrium. So that's all well and good, but what does this have to do with the zeroth law of thermodynamics? Well, let's say you did this. You had your pie and your sphere and you waited until they came into thermal equilibrium, and now you insert a third object into the mix. Some small amount of water or a large amount of water, doesn't actually matter, but some water over here. And so after allowing the pie and sphere to come into thermal equilibrium, which is to say they don't exchange any more heat, you bring this sphere over here, you put it in contact with the water, and for the sake of argument, this doesn't usually happen this way. For the sake of argument, let's say no heat is transferred either way over here, so 2 is also in thermal equilibrium with this water, with 3. Usually you'd have water at some different thermal state and they would exchange heat. But for the sake of argument, let's say that no heat's exchanged over here. That begs a question. You say to yourself, wait, so 2 is in thermal equilibrium with 1, no heat transferred. 2 is in thermal equilibrium with 3, no heat transferred. What if, now you start thinking and you ask, what if I put 3 in contact with 1? Will there be any heat transferred? That's the crux. That's the question that the zeroth law of thermodynamics addresses, and the answer is no. No heat's going to get transferred here either. So the zeroth law says that if object 1 is in thermal equilibrium with object 2, and object 2 is in thermal equilibrium with object 3, then object 1 is also in thermal equilibrium with object 3. This is the zeroth law of thermodynamics, and you can see some of you out there are probably thinking, well, duh, how could it ever not be like that? If 1 is in equilibrium with 2 and 2 is equilibrium with 3, then 1 has to be in equilibrium with 3. Well, yeah, I mean, it is like that. Our universe is like that. But think about it a little harder. You could probably think of a universe where it might not be like that. Imagine a case where, let's take this water, separate these all again. Imagine a crazy universe, which is not ours, where for some reason steel and pie, thermal equilibrium, no heat transferred. Steel and water, thermal equilibrium, no heat transferred. But water and pie, well, not thermal equilibrium. Heat does get transferred. This would be terrible. This would be a horrible universe to do physics in, because now you'd have to have some separate definition of temperature depending on what type of material you have. There'd be a key lime pie steel sphere temperature together, and there'd be a steel sphere and water temperature, and there'd be a water and key lime pie temperature. It'd be horrible. But our universe does not behave that way. Our universe follows the zeroth law of thermodynamics, and the best part is that this allows us to define a universal temperature scale. Because temperature is defined to be the thing that's the same between two objects when they're in thermal equilibrium. In other words, the zeroth law makes it such that I could say this pie is at a temperature of 20 degrees Celsius, and this sphere is at a temperature of 20 degrees Celsius, and this water is at a temperature of 20 degrees Celsius, regardless of me telling you beforehand which two I'm going to put in contact with each other. If I tell you these are all at the same temperature, you know, put any of them in contact, no net heat's going to transfer between them. If the zeroth law didn't hold, you wouldn't be able to do this. You could say that, okay, the pie and the sphere are at the same temperature, 20 degrees. And you could say that the sphere and the water was at the same temperature, call it 20 degrees if you want. But the water and the pie would not be at the same temperature. You couldn't call these both 20 degrees. You'd have to have separate scales, and that's why this would be horrible. That's why you should respect and love the zeroth law of thermodynamics. But why is it called the zeroth law of thermodynamics? Well, physicists had been working on the first law of thermodynamics for a long, long time. They got that pretty well nailed down. Only later did they realize, wait, this whole endeavor of thermodynamics is kind of relying on the ability of us to be able to define a universal temperature scale between all materials and objects, and that's kind of more fundamental than even the first law is. So they realized we should give this a number previous to the first law, but the first law was already the first law, so we call this the zeroth law of thermodynamics.
So I hope you well understand that zeroth law of thermodynamics and its application. Let's move on this next slide. We already discussed the different forms of energy, so we move on. Our short review that we have kinetic energy and potential energy, and subcategory of kinetic we have some thermal energy, mechanical energy, electrical, magnetic energy, but in the potential land we have a chemical energy that has very high potential to produce energy, like we all experience in our car, combustion in planes, in the turbojet engines, the elastic energy in a spring system, like for example when the car experiences some brake or some speed breaker, the spring suspension and spring system stored the energy and then recall when it goes after the bump. The nuclear energy, we all know that from the nuclear energy we have a chain reaction of fission and fusion by which we can produce lot of energy. And of course the gravitational energy. In between that we have a sound energy and light energy that is related to the rays, and we have a different theory of light packets form and rays form. So move on. This is the same definition we already covered. The microscopic form of energy, macroscopic form of energy. The macroscopic is depend on the physical reference of the frame as defined in the definition, whereas the microscope form of energy is independent of the size and the frame of reference. Those for that definition, those related to molecular structure of a system and degree of molecular activity, they are independent of outside reference of frame, like nuclear energy. This is a chain reaction related to the microscopic form energy, that is internal energy of the nucleus. So basically it is the what is microscopic energy? It is the sum of all microscopic form of energy is called internal energy of the system, and in the thermodynamics it is denoted by capital U. The total energy of the system is consist of kinetic, potential, internal energy, and is expressed as delta E is equal to E is equal to U plus PE plus kinetic energy. If we call it as a net total energy, then we can apply with the delta E. Delta E is equal to delta U delta PE plus delta kinetic energy. If we talking about the two different processes of the energy, we have to find out the total energy. So we can express this in this form. Let's move on the another definition. Mechanism of energy transfer. uh, but in the previous slide I'd like to tell you that the total energy is not only internal potential and kinetic energy. This equation is limited to the closed system only. But if we in future slides, in future lecture, we will study open system, so we add more energy in the right reference, but this is limited only up to closed system application. Mechanism of energy transfer. In thermodynamics, mostly the transfer of energy is taken place by the heat transfer. So first of all, we have to study heat. Heat is a form of energy that is transferred between two system or a system and its surrounding by virtue of its temperature difference. The heat transfer to a system increases the energy of the molecules, thus internal energy of the system. So how much the heat transfer taken place in the system, the internal energy of the system will increase. Like for example, in this we have a room temperature of 25 degree and the soda bottle have a temperature of 25, so there will be no heat transfer. We can say it is in the thermodynamically equilibrium. But in later soda bottles, we have seen that the temperature of second bottle is 15 degree and the outside temperature is 25, so it will exchange heat transfer of 8 joules per second. And if we increase the temperature difference, like in this case the soda bottle have 5 degree and outside temperature is 25, so it will take more heat transfer taken place, like 16 joules per second. And it in the thermodynamics it is denoted by capital Q. So let's move on to the next slide. Energy transfer work. Another important parameter is work. Work is the energy transfer associated with the force acting through a distance. For a rising piston, a rotating shaft, an electric wire crossing the system boundaries, all are associated with the work interaction. Electrical work and mechanical. For that, for a particular example, we have a mechanical work. The engine is running. The engine is connected with the shaft, and this shaft is connected with the propeller, which transfer the work into the fluid. This energy is converted into the work, and work convert into the potential energy that moves this boat. It flowing the water in this direction, but opposite reaction taking place in this boat, due to which the boat is moving forward. The same happened in airplanes, but airplanes the flowing fluid is combustion gases, but in this case the flowing fluid is water. And the second application, we have a electrical oven, in which we are applying work in the form of electricity, and this work converts electricity into the internal energy of the oven, that increasing the temperature. So internal energy is directly proportional to the temperature. Now mass transfer. When the mass enter a system, energy of the system increases because mass carries energy with it. So in this case, there is an example of open system. It flowing the mass and it carry the energy which moving that boat. Likewise, when some mass leaves the system, the energy contained within the system decreases because leaving mass take out some energy with it. So this is the mass transfer. In the open system, we will study and we will do numerical related to open system. Now this is a very good example of conversion of energy. In this case, we have an electrical generator. It is suspended with the mass, with the rope and the coupling. When we allow this mass to move down due to its weight, it will rotate this shaft, and the shaft will produce electricity due to the magnetic coil and the coil in the electrical generator. This electricity can be used for the space heating. This is this example, the electricity used by electrical heater, which is increasing the internal energy of gas or liquid. So in this case, the kinetic energy converted into the electrical energy, and that electrical energy, work is converted into directly convert into the internal energy. So now we come to the first law of thermodynamics. This the previous slide is also showing how the energy is transferring from one end to two end. The first law of thermodynamics you already studied in your inter, that energy can neither be created or not be destroyed. It can only change its form. It's called the conservation of the energy principle. Now by this definition, you come across a question that if the energy is transformed from one phase to another, we can produce a perpetual machine. Like in this particular example, the potential energy is converting into the kinetic energy. If we make a system, such system that this kinetic energy we can convert again into potential energy, so it's move continuously. This is a concept taken place in late 15s. I have very good animation videos of perpetual motion that can be used for this particular.
Around 1159 AD, a mathematician called Bhaskara the Learned sketched a design for a wheel containing curved reservoirs of mercury. He reasoned that as the wheel spun, the mercury would flow to the bottom of each reservoir, leaving one side of the wheel perpetually heavier than the other. The imbalance would keep the wheel turning forever.
That I was talking about.
Bhaskara's drawing was one of the earliest designs for a perpetual motion machine, a device that can do work indefinitely without any external energy source. Imagine a windmill that produced the breeze it needed to keep rotating, or a light bulb whose glow provided its own electricity.
Like in this case, the glowing light is transfer light energy into to the solar panel. Solar panel produce electricity which can light up this bulb. So it can continuously run by the concept of perpetual. But in later videos,
These devices have captured many inventors' imaginations because they could transform our relationship with energy. For example, if you could build a perpetual motion machine that included humans as part of its perfectly efficient system, it could sustain life indefinitely. There's just one problem. They don't work. Ideas for perpetual motion machines all violate one or more fundamental laws of thermodynamics, the branch of physics that describes the relationship between different forms of energy. The first law of thermodynamics says that energy can't be created or destroyed. You can't get out more energy than you put in. That rules out a useful perpetual motion machine right away, because a machine could only ever produce as much energy as it consumed. There wouldn't be any left over to power a car or charge a phone. But what if you just wanted the machine to keep itself moving? Inventors have proposed plenty of ideas. Several of these have been variations on Bhaskara's overbalanced wheel, with rolling balls or weights on swinging arms. None of them work. The moving parts that make one side of the wheel heavier also shift its center of mass downward below the axle. With a low center of mass, the wheel just swings back and forth like a pendulum, then stops.
Not only this this problem, center of mass problem, we also have some friction factor over here. Air friction over here, which decreases its velocity, and we need to put some extra energy to continue its motion.
What about a different approach? In the 17th century, Robert Boyle came up with an idea for a self-watering pot. He theorized that capillary action, the attraction between liquids and surfaces that pulls water through thin tubes, might keep the water cycling around the bowl. But if the capillary action is strong enough to overcome gravity and draw the water up, It would also prevent it from falling back into the bowl. Then there are versions with magnets, like this set of ramps. The ball is supposed to be pulled upwards by the magnet at the top, fall back down through the hole, and repeat the cycle. This one fails because, like the self-watering pot, the magnet would simply hold the ball at the top. Even if it somehow did keep moving, the magnet's strength would degrade over time and eventually stop working. For each of these machines to keep moving, they'd have to create some extra energy to nudge the system past its stopping point, breaking the first law of thermodynamics. There are ones that seem to keep going, but in reality, they invariably turn out to be drawing energy from some external source. Even if engineers could somehow design a machine that didn't violate the first law of thermodynamics, it still wouldn't work in the real world because of the second law. The second law of thermodynamics tells us that energy tends to spread out through processes like friction. Any real machine would have moving parts or interactions with air or liquid molecules that would generate tiny amounts of friction and heat, even in a vacuum. That heat is energy escaping, and it would keep leaching out, reducing the energy available to move the system itself until the machine inevitably stopped. So far, these two laws of thermodynamics have stymied every idea for perpetual motion and the dreams of perfectly efficient energy generation they imply. Yet it's hard to conclusively say we'll never discover a perpetual motion machine, because there's still so much we don't understand about the universe. Perhaps we'll find new, exotic forms of matter that'll force us to revisit the laws of thermodynamics. Or maybe there's perpetual motion on tiny quantum scales. What we can be reasonably sure about is that we'll never stop looking. For now, the one thing that seems truly perpetual is our search.
So I hope you like this video, and your concept will be clear with the first law of thermodynamics, that energy can transform from one phase to another but cannot be converted into complete into other form. There will be some losses in terms of temperature, in terms of heat, in terms of friction. Like for example of a car, if we cannot convert the whole chemical energy into the kinetic energy, because during this interaction, when the combustion take place, lot of energy waste in the form of heat that we are experiencing in our car. We need to place a radiator in the bigger engine. For the bicycle engine we don't need any radiator, but for the car and the heavier engine we put radiator, which cool down the engine and releases the lot of heat into the environment. So this is the basic concept and idea of the first law of thermodynamics. Let's move on. The general energy balance, what we study, that the total energy, the net heat energy is equal to the energy entering to the system minus total energy leaving the system, is the change in the total energy of the system, that I already written in the previous slides and below the equation. So the net change, increase or decrease in the total energy of the system during the process, is equal to the difference between total energy entering the system and total energy leaving the system. We are talking about the closed system right now, but in the later, when we move on the open system, there will be much more variable in it. So for this particular example, we have a pressure cooker. We are giving the heat transfer of 5 kilojoules, that increase its kinetic internal energy. So the total net change in the internal energy is only its due to the heat transfer. That's why delta E is equal to delta Q, and the sum of the heat is releasing in from the into the surrounding from this boundary. The dotted line is shown here is the boundary of the system, and the inside portion is our system. So it is taking heat from the environment and also releasing heat, some of the heat in the environment. So delta E in minus delta E out is equal to delta E of the system. So the change in the total energy of the system could be the E is equal to E initial minus E final minus initial. So we put delta in the sum of all of energy, the like internal energy, potential energy, delta PE and delta KE. So the total energy, the change in the total energy will be is equal to the change in the internal energy, the change in the potential energy and change in the kinetic energy. Most systems encountered in the practice are stationary, that is they do not involve any change in their velocity or elevation. For elevation we can point out with the potential energy, and velocity we can point out with the kinetic energy during the process. For a stationary system, the changes in the kinetic and potential energy will be zero. So the delta the net change in the total energy will be the change in the net change of the total energy is equal to the net change in the internal energy. For that system, we have developed equation in thermodynamics. We are not doing its derivation, we directly use this equation. Delta E of the system is equal to Q net, the heat transfer, the net heat transfer and the net work done in the system. So the change in the amount of the energy contained within the system during the interval is equal to the net change of the energy transfer in across the system boundary by heat transfer during some time interval. I will correct its words. The net amount of the energy transfer in across the system boundary by the work during some interval. So this is the equation we will using in the numerical, but we have a sign convection in the particular system and you have to remember it. If you don't, you make mistakes. Mostly I taught this BME course in civil, in urban, in electronics, in electrical. Students do make mistake with due to this sign convention. If you do not remember the sign convention, you will make mistake in the numerical and it will give different answer. So first of all, the heat transfer will greater than 0 means we will use sign convection positive when heat transfer to the system. Like in previous picture, the here is the heat transfer to the system. So in this case we have to put Q in with the positive form. And heat transfer from the system, it is example of this is heat transfer from the system, this is heat transfer to the system. So we can correlate the idea. It will help you to remember this positive and negative sign. The internal energy depends upon the total internal energy, as in the closed system when it is not moving or it's not getting elevation. So the heat transfer increase its internal energy, so we put with the positive, and when the heat loss from the system, its energy will be decreased, so we put the sign of convection minus. Unlike that net heat the heat transfer, work done is opposite to it. If work done by the system, we put positive sign, but if work done on the system, we put negative sign. Why? Due to this negative in the equation, so it work oppositely. So let's move on towards its numerical. First numerical, it is very easy numerical. Example 2.10 from the book Sangil. This is a picture in which the rigid tank contains a hot fluid that is cooled while being stirred by the paddle wheel. Initially, the internal energy of the fluid is 800 kilojoules. During the cooling process, the fluid loses 500 kilojoules of heat. That is shown in the figure. 100 kilojoules of work applying by the paddle, and it will losing 500 kilojoules outside the from the system to the surrounding. So this by steering it will lose its temperature, and due to the temperature internal energy is decreasing. So the paddle wheel does 100 kilojoules of the work on the fluid. Determine the final internal energy of the fluid. Neglect the energy stored in the paddle wheel. So by looking this picture, we get an idea that internal energy will decrease, because it is we are giving less energy, and more energy is releasing in this way. And in the similar way, when for an example, when we stir the tea, the temperature of tea is decreased to the comfortable level of drinking. So let's it start its numerical. We can play slide 2. So the equation is delta E is equal to Q minus W, and the delta E is equal to sum of delta KE plus delta PE plus delta U is equal to Q minus W. We know that it is not gaining any elevation, so it is 0. It is not taking any velocity, so it is 0. The delta U is equal to final internal energy minus initial energy, so U2 minus U1 and Q minus W. How much the work done applied on the system? Oh, sorry, in this case it is not gaining any heat, it is releasing heat, so we put this sign with the minus. And how much it is releasing? Go back to the numerical, 500 kilojoules. So we can write 500 over here, and this sign is related to the equation. We cannot change this sign, but after that we change the sign according to its sign convention. So in this case, work is added to the system, not work done by the system. So unlike in this system we have opposite case. So when the work done by the system we put positive, but when the work is done on the system we put negative. So we put here negative 100. So minus minus plus, U2 U1 is 100 kilojoules. So we didn't write its unit. You have to write its unit also, okay? So minus 500 minus minus plus, so it is positive 100. Minus 800 goes there with the positive sign, and 500 it is plus 100 minus 500 is minus 400 kilojoules. So the answer will be 400 kilojoules. So this is the answer. Here the answer 400 kilojoules. It is very easy numerical. I hope you will get the idea and easily solve in the paper. So this lecture number 5 hold till here. In the next lecture we will do some more numericals, inshallah. Okay, Khuda Hafiz.